Okay, so what we're going to do is we're going to take one more look at trig equations. So this is section 8.4, day 3. And we're going to take a look at a couple of quick examples that show you some of the more oddball kinds of problems that we do run into from time to time. So the first thing we're going to take a look at is we're going to take a look at the following problem. So example 1, and we are going to solve sine of x plus cosine of x equal to 1. And we're going to solve that on the interval 0 to 360 degrees. Now notice that it's a closed interval on the left side, an open interval on the right side. That means that 0 degrees is an acceptable answer, but 360 degrees is not an acceptable answer. So if we get 360 as one of our solutions, we have to throw that out. Notice also we are going one time around the circle, and we want our answer to be in degrees. That's very important. The issue with this problem, the one that makes it strange, is that we don't have sine squared or cosine squared. And so therefore, we cannot actually take this thing and make any of our Pythagorean substitutions. We need square trig functions for that. Also, we have no way to change sine into cosine or cosine into sine directly. So we're kind of at a loss here. This thing doesn't factor, so we have no way to really go about solving this thing other than trial and error. And that's unacceptable. So what you want to do on a situation like this is you want to look at this and square both sides of the equation. When you do that, remember that this does not become sine squared plus cosine squared. You have to FOIL this out because there's more than one term inside. Don't make that mistake. This becomes sine squared of x plus 2 sine of x cosine of x plus cosine squared x equals 1 squared, which is 1. Now we have some squareds involved, and what happens here is really nice. If we take a look at sine squared x plus cosine squared x, we know that that is really equal to 1. And so this then becomes 2 sine of x cosine of x plus 1 equals 1. We subtract 1 from both sides, and so we get 2 sine of x cosine of x equals 0. Divide everything by 2 on both sides, and we get sine of x cosine of x is equal to 0. We now have something that's factored. It's equal to 0. We can then set each factor equal to 0 individually. And what this now allows us to do is this now allows us to solve for each of these as individual equations. So if we stop and take a look at these, draw your little picture, sine of x is going to be equal to 0 here at 0 degrees and over here at 180 degrees, both of which are acceptable answers here. Cosine of x is equal to 0 up here at 90 degrees and down here at 270 degrees. Now notice on this first one, I did not put 360 degrees as a possibility. The reason is we had the round bracket here, so 360 is not an acceptable answer. This has to get tossed out, so that's why I didn't write it in the first place. Had this been a square bracket, I would have had to include 360 degrees as one of our solutions as well. Had this side been a round bracket, I would have had to throw the 0 out, and 180 degrees would be the only solution that we get from this one. So what we end up with is we end up with, excuse me, we're not using theta, we're using x. We get x is equal to 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Now there's an issue that pops up here that popped up on one of our problems yesterday, or on the last homework assignment, I should say. And that is that we have the potential here for extraneous solutions. You've got to plug each of your answers back in and see if they actually work or not. Why would we get extraneous solutions? Because we squared both sides of the original equation. And what happens when we square both sides of an equation, you learned this in Algebra 1 and again in Algebra 2, and we've talked about it this year, is you have a tendency to kill off negatives when you square things. although we didn't see the negatives, we certainly could have killed off negative values. We don't know what x is, so we have no idea if sine of x or cosine of x are equal to negative numbers. They certainly could be. So it's very important anytime you square both sides of an equation, you definitely have to check for extraneous solutions. So if we take our sine of x plus cosine of x equals 1 and plug 0 in, sine of 0 is 0, cosine of 0 is 1, 0 plus 1 equals 1, so this one works. If I plug in 90 degrees, sine of 90 is 1, cosine of 90 is 0, this one also works. If I plug in 180 degrees, sine of 180 degrees is 0, but cosine of 180 degrees is negative 1. And clearly 0 plus negative 1 is not equal to positive 1, but if I squared both sides, I'd get 1 equals 1. So it's a solution to the squared version, but not the original unsquared version. So therefore, this one has to get tossed. Likewise, at 270, sine is negative 1, cosine is 0. This equals negative 1 again, so this is also an extraneous solution. So because of that, sorry, some of you may have still been copying that. Because of that, our only two actual solutions to this original equation are 0 degrees and 90 degrees. So it's very, very important. If you do square both sides of an equation, because of square roots or because you're trying to figure out a way to make some substitutions using the Pythagorean identities, you've got to make sure you check in the original equation for extraneous solutions. So that's the first of our oddball equations. Next one is not such an oddball equation. We do run into it quite frequently, but we haven't talked about it yet, and that is example 2. Not example 2 from the book, just example 2 from this particular video. And that is we want to solve sine of 3x is equal to 1 on the interval 0 less than or equal to x less than or equal to 2 pi. Notice this time there's an equal on both, so 0 and 2 pi are both acceptable solutions. We have no idea if that's going to come into play or not, but they are acceptable in terms of the domain restrictions here. So what we're going to do is we're going to ignore the 3x for just a moment, and we're going to just take a look at sine of theta equals 1. And let's see what answers we would get if that was our equation. Well, sine is equal to 1 right here in radians at pi over 2 radians. And that's the only place on the circle where we get this value. The problem is, though, that we don't have sine of theta equals 1. So this would give us theta is equal to pi over 2, right? Our angle is equal to pi over 2. Well, that concept is what we're going to use here. The problem is that we don't have a single angle. We have 3 times our angle. And so what ends up happening now is that this now gives us 3x is equal to pi over 2. Right? Our angle, instead of being theta, is really a 3x. So it's 3x that's equal to pi over 2. Problem is, we don't care what 3x is. That's not what they asked us to solve for. They want us to solve for x. So we're going to have to get x by itself. We have to get rid of the 3. But before we do that, there's a very important adjustment you need to make. And we've talked about this before with some of our half-angle stuff. If x is between 0 and 2 pi, and our angle that we're working with is currently 3x, then 3x must be between 0 divided by 3 and 2 pi divided by 3. Sorry, let's refresh that. 0 times 3 and 2 pi times 3, which is 6 pi. So now what happens is we can't just stop one time around the circle. We can't stop at 2 pi. We have to go all the way out to 6 pi. What does that mean? That means that we are going to go 3 times around the circle. So the first time around the circle, from 0 to 2 pi, we get an answer of pi over 2. The second time around the circle, we're going to go all the way to 2 pi, and then an additional pi over 2. And so we're going to take pi over 2, and we're going to add 2 pi to it to get a coterminal angle the second time around the circle that has the same coordinates. So we have to get a common denominator, so that's really pi over 2 plus 4 pi over 2. that equals 5 pi over 2. So that's also another solution. So this was the first time around the circle. This is the second time around the circle. Now we have to go a third time around the circle because that's what the 3x is doing to our interval here. So we're going to add 2 pi again, which is another 4 pi over 2 when we get a common denominator. That gives us 9 pi over 2. And so do you see we can do this over and over and over to get around the circle as many times as we need to. If you got 2 answers the first time around the circle, which is typically going to be the case if you're not on one of the axes, then you're going to add 2 pi repeatedly to each of the different solutions that you got the first time around the circle. And so if you started out with 2 solutions, then the second time around the circle you would get 2 more for a total of 4 solutions. If you had to go 3 times around the circle, you'd get 2 more for a total of 6 solutions. This particular one, since it only gave us 1 answer the first time around, is going to give us 3 answers 3 times around. So these are the different answers that we get for 3x. Now notice that x has to be between 0 and 2 pi. These are not all between 0 and 2 pi. Only this one is. But that's still 3x. What we now have to do is we take our 3x equals whatever our collection of solutions are for our 3x angle. And now we're going to have to divide everything by 3. And another way of thinking about that is instead of dividing by 3, we can really just multiply by 1/3 to get x by itself. And so when I multiply the other side by 1/3, what I end up with is the following 3 angles. Pi over 6, 5 pi over 6, and 9 pi over 6. But 9 pi over 6 simplifies down to 3 pi over 2. So these would be your 3 final solutions. So you would write x equals pi over 6, 5 pi over 6, and 3 pi over 2. This is how you deal with multiples of angles. So a 3x means you go 3 times around the circle. A 5x means you go 5 times around the circle and then divide by 5 at the end. A 1/2 x means you'd only go halfway around the circle. You'd only collect answers from 0 to pi. And then to get rid of a 1/2 x equals some angle, to get x by itself, at the end, you would multiply by 2 rather than dividing by 2. Okay. So that's the idea. So that's example number 2 with a multiple of an angle. Now let me show you one other problem, and then you can go ahead and use that on the next assignment. What if we were solving 2 sine x cosine of x is equal to negative square root of 2 over 2. And we want to solve this for all x. So for all x in this interval, the open interval 0 degrees to 360 degrees. Again, it's all x in that interval. We're only going 1 time around the circle, so there won't be any plus 2 pi k or plus 360 degrees k. Although if it said just all x and didn't give us the interval, we could obviously just glue those on to the end of our solutions. The problem here is that I can divide both sides by 2, which gives me negative rad 2 over 4. But having something factored, something times something equals a number that's not 0, doesn't help me proceed from there. I can't solve it. So what we're going to do instead is we're going to take a look at this and say, wait a minute. I can't make any substitutions using the Pythagorean identities, but I can make a substitution. What is 2 sine x cosine x equal to? We've learned that that's an identity for sine of 2x. And so what we have now created is we have now created one of those multiple angle formulas or multiple angle problems, just like example number 2. So since x is between 0 degrees and 360 degrees, 2x now is going to go between 0 degrees and 720 degrees. In other words, 2 times around the circle. So what we're going to do is we're going to take a look at what 2x has to be in order for the sine to give us negative rad 2 over 2. Well, sine is negative in these 2 quadrants. Rad 2 over 2 is the 45-degree angle in each quadrant. And so that's going to be 180 plus 45 is 225. And this is going to be 360 minus 45, which is going to be 315 degrees. We have a 45-degree reference angle. Sorry, my tablet's not cooperating. Let's let it catch up with us here. Actually, let me just restart my tablet. Bear with me just a moment. I apologize for that. All right. So we get 45-degree reference angles. So 360 minus 45 gives us 315. 180 plus 45 gives us 225. Those are the two places where sine of theta is equal to negative rad 2 over 2. So we get 225 degrees, 315 degrees. That's the first time around the circle. Now the second time around the circle, we're going to get two more answers. How do I find those? I add a full circle to it. So I'm going to add 360 degrees to this one, which gives me 585 degrees. I add 360 to this one, which is going to give me 675 degrees. Now I've gone two full times around the circle because of the 2x. Now I'm ready to solve for x. And to do that, I'm going to take 2x equals all of these, and I'm going to divide everything by 2. So I'm going to grab my calculator real quick, and I'm going to do 225 divided by 2 gives us an answer of 112.5 degrees. That's the first angle. And let me punch in the rest of these. 315 divided by 2, 585 divided by 2, 675 divided by 2. And so I end up with 157.5, 292.5. And my last one was 337.5. Notice that while not all of these were between 0 and 360, all of my final answers for x are between 0 and 360. And so when I multiply them times 2 and then take the sine of that, I am going to get my negative rad 2 over 2. So those are the final solutions. So that's how you do a couple of these other kinds of examples. Hopefully that will give you some assistance getting through these problems and kind of solidify your understanding of solving various types of trig functions or trig equations.